All right, so we were wrapping up the median yesterday and talking about all the properties of median. So let's jump right into mode. What does mode mean to y'all? What is it? Good. Mode means most often. So most, right? Median was what? Middle, and then mean was what? Average, right? And we had two different averages. We had population, which is the little mu looking Greek letter. And then we saw that the sample was the Roman X to represent the sample of the population. All right, so for mode, the mode is the value of the data that occurs most often. Data sets that have only one value that has the greatest frequency, most, M-O-S-T is how you spell most. Greatest frequency are called unimodal. Right, so data sets that have only one value that has the greatest frequency are called unimodal. Basically, if we were to graph it, there would be only one peak. All right, that's what unimodal means. All right, any questions there? So let's do an example. Okay, that's valid. And what was the answer? It was nomial. All right, I'll give the point back. Yeah. Yeah. But that was my argument too, because that's what I put. And then when I saw that they put ordinal, I was like, okay, that is seen. So I gave y'all like a freebie there, anyways, out of 5. But yeah, if you end up missing 2, I'll give you the point back. Remind me Thursday. Yeah. So bring the test and your proof as well. With the ratings of the PG. Okay. So I saw the word rating, and I instantly went ordinal as well. It'll go up by 1 point. Yeah. Oh, it only took a point off. Now, if you missed other ones, that's different. Well, that's what I ideally did. But if you missed 2 and that was the specific one, I'll give that 1 point back. So if you missed that one, but you didn't, you was already a wash. So it didn't improve. There you go. All right. So again, I do reward points if you have a valid argument, because in statistics, I do feel like we'll have some valid arguments. In college algebra, it was like this is the answer, and this is like it's like black and white. There's so much gray in statistics, like, but that one I ended up getting that one wrong too. So, all right. So in this example, it says find the mode of this unimodal sample. Basically, what you want to do here, you could do a frequency chart. You could put this from least to greatest and just see, with this data being so small, what is the most occurring number? Right. All right, so in this solution here, it says there's, so we got what? 10, 10, and 10, and then there's no other repeating decimals. So there is only one mode, because you can have modes that have multiple modes, like if they have the same amount of frequency. So this sample is what we call a unimodal. There's only one number out of all of them that has the greatest frequency. Now, let's say, for instance, let's say I added 14 there. We only had 14 twice. 10 would still be a unimodal because it's still the highest. It'd be different if I then added another 14. Then I would have 2 modes, because it would be 10 and 14, and then the sample would be bimodal, right? So it can have repetitive numbers, but we're looking for which one has the highest frequency. And if there's only one, it's called a unimodal. What's your question? Did I answer it? Gotcha. So this didn't exist, but if it did, that's what it would have been. We'll get to there. We're getting there. All right. So again, 10 would be the answer, and bless you. And it's because it occurred 3 times. I will say I wouldn't count off for this, but they are specific since the decimals do say 10.0. Make sure you also write 10.0 with your statistics. All right, so this is just which is more than any other value that appeared. So data sets that have exactly two values that occur at the same time, at the same frequency, same greatest frequency. Let's get the word right. Then again, we're called bimodal. So like I said, if I would attach two more 14s there, then I would have two modes and it would have been bimodal. Does that make sense? And I think if it goes more than that, I think it's just called multimodal or something like that, but we'll see. Any questions? We're good? Very straightforward on the definitions there. All right. So in this example, I want you to find the modes of a bimodal sample. So let's do this. So I see a 104 once, twice, 3, 4 times. So 104 has a frequency of 4. Oh, good. Missed it. 5. I got a 107 one time. I got a 109, 1, 2, 3, 4, 5. So 109. I got 5. And then I got a 110 one time. I got a 111 2 times. And then a 112. Is it delayed again? Oh my gosh. We had second period was perfectly fine, but first period I literally did the whole problem and I looked up there and it was still on the other problem. Like it hadn't even done the next problem. So I was like, I see why you are lost now. All right, so here we see that we have two modes because these have the greatest frequency. So when so the solution here is the values are 104 and 109. Those are your two modes, and it's because they occur 5 times. There you go. So the values 104 and I guess I should have said the mode are the values 104 and 109 because occurred 5 times. And you could add there too a little extra 5 occurred 5 times, which is the greatest frequencies. I think for your homework and on your test, they'll just ask you what the mode is, and you'll just write the numbers down. Is that right? That's a Y at the end, not a T, as you know. Oh, okay. Oh, gotcha. It was real bad last first period. All right, so when a data set has more than two values, again, that occur with the same greatest frequency. So again, more than, I was right. So more than two values, it is called multimodal. So it's unimodal if it only has one, uni meaning one, bimodal if it has two. If it has two or more, or sorry, it has more than two, then it's just multimodal. We don't have like a tress or a whatever the next one is. Yeah, we don't have any of those. You kind of see that kind of happen a lot in math. We just kind of go, yeah, we're gonna stop here, and the rest of them are all gonna be the same answer. Any questions on bimodal? Make sense still? So mode can have multiple answers. Median and mean cannot. So in this example here, let's look at a multimodal sample. And it says in example 3.2, 3 values occur 6 times, which is the greatest frequency, which means the data set is what? Oh, it did. No, yeah, it would be. So it kind of gave us a little answer there. So it'd be multimodal. And then the next part says there are blank for your solution. So there are your blank here, because I don't feel like going any further, would be 3 modes, because we have 3 of them, which are, and that's what we got to determine. So is this in least to greatest? Oh, that makes life so much easier. Did we do this one already? These numbers look familiar. I think we did, didn't we? When it said 3.2, was that that was the median one, yeah. The calories of dressing. Cool. So, and so we can see that we have 1, 2, 3, 4, 5 for 100, just 2 for 110, 1 for 115, 1, 2, 3, 4, 5, 6 for 120, 1, 2, 3, 4, 5, 6 for 130, and then 1, 2, 3, 4, 1, 2, 3, 1, 2, and then 1, 2, 3, 4, 5, 6 for 160. So even though 5 was pretty up there, 6 would be the greatest frequency. So our answers would be what? Perfect. Questions? Pretty straightforward still. Nothing too challenging. I like to say this gets harder, but it doesn't. So if you're looking for a challenge. Is it? Oh. See, words are just ridiculous. I'm not a big word person. All right. So some data does have no mode. And this happens when all the values occur at the same frequency. So that's actually most of our data will happen. So like if we look at these numbers here, notice that none of these have the same number. So this right here would mean that there is no mode, right? If only one of them would just repeat it, then we would have a mode. But since they all have the same frequency, there is no mode. Again, so the mode is the only measure of central tendency that can be used to find the most typical case for nomial data. Alrighty, so then let's go into example 3.7, which is sales for fast food franchises. In 2.7, we have nomial data of worldwide sales in billions of dollars for fast food franchises in a specific year. I remember kind of doing this on the last chapter, but they have 8.7 million for Wendy's, 14.2 million for KFC, 9.3 for Pizza Hut, 12.7 for Burger King, 10 million for Subway. And it's asking us the category which the greatest frequency is what? So we have nomial data of the worldwide sales in billions of dollars for fast food. What data tables are we looking at? So we have a nomial data of worldwide sales in billions of dollars. Category with the greatest frequency. I don't know. This example here says we have nomial data of worldwide sales in billions of dollars for fast food. It seems like what they're doing here is they're calculating this as not their revenue. I guess it would be the revenue, but that would be their frequency. Yeah. And so this ends up being a frequency chart saying that KFC sold 14.2 billion dollars worth of food. So they counted up all these food items. That's a bad chart. Again, we've talked about misuse of statistics, but so it would be KFC. This to me, if I look at this, I'm going, this is how much they made. Yeah. So this would be, all right. So this is a frequency chart. They need to be specific with that with our titles, but it would be KFC. K comes first. Thus, the most typical case is, 14.2, because that would be the number, meaning the mode is KFC. So the category with the greatest frequency is KFC. Thus, the most typical case is 14.2, meaning the mode is KFC. Right. Well, this is because this is a frequency table. It's what they're trying to tell us, but they didn't label this correctly. So this dollar sign should have gone away. And that means that this would happen 8.7 times. This happened 14.2 times. This happened 9.3 times and stuff like that. Yeah. Because I would have done the same thing. If this would have been a homework question, I'd been like, no, they're all done the same. But yeah, bad use of a graph or a table. All right. So let's review some of our properties of mode. The mode is used to find the most what? Typical. Typical case. Meaning, is it a bimodal, unimodal, multimodal? What is our frequency chart going to look like? So the mode is the easiest average to find because we're looking at just which one happens the most, no math involved, except for maybe putting least to greatest, but even that doesn't matter. So the mode can be used for qualitative and quantitative data. Or sorry, variables. The mode is not necessarily unique because we can have multiple answers and may not even exist. Right? Because we saw some that didn't have any mode because they were all the same frequency. So it's not you. It can be unique, but it cannot be unique, and it could be none. Right? Questions on mode? Right? I feel like finding the mode's easy, but some of these vocabulary questions get a little tricky. All right, so resistant measures of central tendency. So a measure is resistant when an extremely high or extremely low data value does not change the value of the measure. And so we have seen that the median is not affected by this resistant measure that y'all don't know is called an outlier yet. And we also saw what is resistant from any outliers. The mode, right? It didn't the if it has an outlier, it didn't occur unless that outlier happened multiple times, and then it wouldn't be an outlier because obviously there's like more of an average there. So median and mode are resistance to outliers. However, extreme values also called, there's the word finally, called outliers can have striking effects on the what? What's the other one we talked about? Mean. The mean can be affected tremendously, either pulling the average up or down. We will learn how to determine which values are outliers later in this chapter. So we kind of talked about that on Monday as well. Any questions so far? So outliers do not affect median mode, but it does. Median mode, but it does affect the mean. So in example 8, it says, find the measure of central tendency of all this information. So it says the following data set has a value much higher than the rest. Which would be which one? 240. When the largest value is deleted from the data set just becomes this. Basically, we remove the outlier. So now we're going to find the solutions of the central tendency, then compare and contrast these values. All right, so in the beginning, it says the measure of central tendency for the first data set is what? Have we done these already? Any of these? I feel like we did these. I don't think so. So we need to go find, oh wait, we don't have to do too much here. It just says find the measure and then compare. So here's just the measure of central tendency for the first. All right, so the mode, what's the most occurring thing here? There's no, repeat it? Yep. Yeah, this will just be no mode. Yeah, so I guess none. And then this one, so the median, is this one least to greatest? It is not. So let's put this in least to greatest real quick. All right, so this one for the first one would be 122, 141, 149, 153. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what's my number? That's going to be my median. Which one? the sixth one. So 1, 2, 3, 4. Let's keep going a little bit more. That's 155. The next one will be my answer, which looks like 157. Yep. Perfect. All right, now we can find the mean. I'll leave that to you. These are easier numbers. So what's the mean y'all got? Okay. 0.5. Yeah. Perfect. All right, and then it then says the measure of central tendency for the data set without the higher value. So what is the mode if we took that 240 out? Still none, did not affect it. What was the median? It would change. So if we take that out, oh yeah, it's going to be 5 this time. So it'll be 5 on both sides. So what was the order? It was 120. I don't know, 122. Gotta do this math again. 141, 149, 153, 155, 157. So that'd be 5. So it'd be this number right here. So it'd be 156. Did we? Yeah. And now the second data set from on the second page. Basically, the second one was when we took 240 out. So I'm going to go and I'm going to do some reverse math here. Check this out. If I divide it by 11, I'm going to multiply it by 11, but go back to my original number. And then I'm going to subtract that outlier, which is 240. And then I'm going to take that and divide it by 10. Rather than have to add them all up again. You can add them all up again too. I mean, it ain't that big of a deal. Hold on. Yes, I'm just get the calculators in my way now. So it'll be 157. So I feel like our definitions over there where median wasn't affected. I don't know. I feel like our median changed. Technically, if the outlier happens to repeat one of the numbers, but I will say in my experience, it don't typically change because if it's an outlier and it's repeating, it's probably not an outlier. Your outlier is probably something that's lower or higher wherever you're at. But I'm not saying it couldn't occur. We could have two freak outliers next to each other. Yeah, I mean, it could happen. It could happen. It could be just two extreme cases. All right. Any questions then on that? So again, notice how much the mean changed. So we went from what was the original, like 164, right? We had 164.5, and then it changed all the way to 157. So our mean got changed a lot. Our median did change, but not by too much, right? It was 157 to 156. So the error there is not too terrible. And it does say that how close to the median of the data was pretty close there. Now, the next thing we're going to go to is Charlie's favorite topic, mid-range. Flat Earth. I like that. All right, so the mid-range, which is also known as capital MR. So this is some notation you would see for mid-range, capital MR, is the arithmetic mean of the lowest and highest values in the data set. It is the midpoint of the range. It is not efficient nor resistant. However, it can estimate the center of a uniform distribution, basically saying kind of where the center of your graphs are going to be, maybe where you have a peak or something, maybe. But it's just going to be the lowest value plus the highest value divided by 2. All right. So if we take this original data that we just had, let's go find the mid-range for it. So here's our original data. So all we have to do is take our handy dandy calculators. I hope. There you go. And what is my lowest value? 122. What's my highest value? Add those up, divide that result by 2, and we get a mid-range of the original set of 181. Questions on how to find the mid-range. Again, if you want to write some math out here, this was 122 plus 240 divided by 2. That's how we got that answer. One more time. 8 within inside of the boundary. I don't, I'm not following. Is 8. Oh, gosh, I was hearing there's only 8 of these in the boundaries. And I was like, well, that's true because 122 is probably an outlier, but you don't know that yet because I haven't taught it. But I was like, well, maybe you got ahead. I was like, okay, yeah, I got you. Looks like an absolute value of 8. I see now. I want to blame it on old age and not hearing. All right. So now we're going to find the mid-range of the data afterwards. So I'm going to write it the answer there. But again, we're just going to take our 122 plus what's our highest value once we take 240 out? 189. And now divide that by 2 and look how much of a drastic change our mid-range is. Because now we have one. Oh my goodness. This is making me mad. Clear. All right. So this was 181 and then we just got, what was the answer? 155. But this time we had to do 122 plus 189 and divide that by 2 versus the 122 plus 240 divided by 2 to get that one. Right? But notice how big of a change it is by taking out an outlier. All right, so it is reasonable to use the mid-range as a descriptive statistics for this data set. I wouldn't know. It could be used as a descriptive statistics for the edited data since the values are fairly close to the median. So what we want to do for our central tendency is we want all of these M's to be relatively close, and then we know we're doing something right. We want the mean, the median, the mode, and the mid-range to all be relatively close. And we can see here at 181, it wasn't, but when we take that outlier out, 155 is close to, what was it, 156 for the median, and it was 157 or something for the mean. So all of these were close. It didn't have a mode, but it's not something that's tallying away from us. So again, right there at that end, you could use it for the second set of data. Right? Since all of them were about the same. Right? Had it been really skewed up or down, then obviously we want to stay away from it because it's just telling us a different story. Any questions on that? All right, so let's review mid-range real quick. Make sure we have it all down. So that's where your answer would go, is right there. All right, so the mid-range is easy to compute. The mid-range gives the mean, or what they also call the arithmetic average. So it gives the mean of the range, right? Mid-range would be the mean of the range, and the mid-range is affected by outliers. Right? And we saw that as well. So mid-range and mean definitely really affected by outliers. Questions on any of this? So let's go study some shapes of graphs now. That part I will say gets a little tricky on some of these things. All right, so there we go. So shapes of distributions. So in chapter 2, many different shapes of different distributions were discussed. The three most important shapes to consider are those that are positively skewed, symmetric, and negatively skewed, which we now know is in the reverse order of our brains. Symmetric just being even. All right, so for positively skewed or right skewed direct distribution, most of the data falls to the right of the mean. So remember, we think positive like going up, but it actually does the opposite, and all of our data is really on the right side. Right? Yeah, to think backwards. I'm telling you, this part right here doesn't make any sense. Right skewed totally makes sense. It's all to the right. But positively skewed and it looks like a negative slope makes no sense to me. Oh, this one here? I think this is not the one up here. No. Most of the data falls to the right of the mean. No, this would be left skewed. Oh my goodness, you're right. All right, so okay, let's keep reading then. So of the mean and clusters at the lower end of the distribution, so right of the mean. So most of the data falls to the right of the mean and clusters at the lower end of the distribution. The tail stretches out to the right. You're right. No, you're right. This is the right skewed. Yeah. So the mean will be to the right of the median, and the mode will be on the left of the median. Most of the data falls to the. Oh gosh, that makes sense. Helps if your professor writes everything correctly. Lefts of the mean. So most of the data falls left of the mean. Yeah, I don't know. Dyslexic doesn't always help. Because I was super confused. I was like, according to this definition, but if I write the right words down, it helps. All right, so one more time, let's read this together. So positively skewed or right skewed distribution, most of the data falls to the left of the mean, which we can see here, and clusters at the lower end of the distribution. So a little cluster here. The tail stretches to the right. So this is like a tail. Like you can think of like this as a dragon. And there's a tail, turtle, whatever you want to call it. And so then the mean will be to the right. So we see that the mean here is to the right of the median and the mode is to the left of the median. Then the mean is pulled towards the tail by more extreme values. So that means that these high outlier values is pulling the mean away from the original data. All right. I feel like I just made a puppy dog. Any questions now that I try to confuse you? Yes. There you go. All right. So let's look at the next one. I'll make sure to copy the right words down. Next semester, I want to be really good at this. All right. All right. So for negatively skewed or left skewed distribution, most of the data falls to the right of the mean and clusters at the upper end of the distribution. The tail stretches to the left. It's one of those. All right, so the mean will be to the left of the median this time, and the mode will be on the right of the median this time. And as before, the mean is now being pulled towards the tail by these extremely low values of distribution. So any questions on those? All right, the last one was our symmetric one. So again, here you go. So here's your negative skewed or right skewed, right? Or is it left skewed? I done lost it now. Yeah, left skewed. And it's left skewed because these data is pulling the mean to the left, right? Even though all our data is here, these values are so low that's pulling it to the left versus the other one, it was pulling everything to the right. So right skewed. Right? We just get, I get it kind of confused just because I see more over here. You would think it wouldn't affect it much. All right, so in our last one here, and this will wrap up 3.1. For symmetric distributions, the data values are distributed evenly on both sides of the mean. The distribution is unimodal, with the mean, mode, and median are all equal at the center of the distribution. So all of these values are going to be the same. Now, I will say we can still have unimodal graphs and they not be exactly the same, but like 1 or 2 digits off, right? It won't be perfect like that, but maybe like one of them's like a little off. All right, so let's get into yesterday's topic now that we finished Monday's topic, which is 3.2 measures of variations. So in this objective 2 here, we're going to describe data using measures of variations such as the range, variance, and standard deviation. So you're going to have some more formulas here, but it's not too terrible on it. So in this example 10 here, fading time of outdoor paint. Considering the sample of time in months, 2 brands of outdoor paint last before fading. So just so you know, people get paid to do this, to just watch paint dry. Fade away. I don't know, but it's enough to make a whole thing about it. All right, so we got brand A and then brand B of all these times and months for the 2 brand outdoor paints to fade. And it wants us to calculate. Oh, I'm going to need both. I need to know the data. All right, so this is going to calculate. It wants to calculate the sample mean time in months to fade each board. So let me calculate this. So it realized that we have sample because we have this Roman numeral 10 here, a brand A. So I'm going to catch up to you. And I'm going to find the mean as it asked. And it was 10 plus 60 plus 50 plus 30 plus 40 plus 20. Divide that by 6. 35. Yeah, pretty quick and easy. I don't know. Let's find out. So on this one now, we have 35 plus 45 plus 30 plus 35 plus 40 plus 25. Divide that by 6. We do, in fact, get 35. All right, so again, it does say, notice that more information is needed to describe this set because all we know is their average and they're both the same. So in this case, we're like, all right, there's no difference in brand A and B. There could be some outliers in there, but we can't assume anything right now. All right, so then it says range. So if you don't know range, range is basically the highest value minus the lowest value. We're not dividing anything. It's literally just taking the highest and subtracting it from the lowest. You'll also see range with just a capital R. So there's some notation there. And now it asks us to find the range of brand A and brand B. So to find the range here, I got to figure out what is the highest value in A. What's the highest value in brand A? 60, good. What's the lowest value in brand A? 10. So what's 60 minus 10? 50. So the range there is 50 months. But brand B, what's the highest? And then what's the lowest? 25. So 45 minus 25 gives me 20. So there's only 20 months between brand B's arrangements. And it says, although the means are equal for both brands, the ranges are quite different. There's a big jump there, which in my eyes tells me I'm thinking we have some outliers. Well, let's see where this story takes us. So we're not assuming anything yet. All right, we'll get there though. All right, so let's talk about population variance and standard deviation. So statistics uses the standard deviation as a more meaningful statistics than range to measure variability. Just to give you an idea, and I don't know if these notes are going to do it or not, but this is what standard deviation is. Let's say here's our graph. Let's call it Unimobile. Let's hypothetically, right? So here's your mean. A standard deviation just represents where you fall on the quartile and stuff like that. So basically what it'll mean is if this is one standard deviation, and you see it with SD, but you also see it with this little cherry thing. We'll talk about that here in a second. And then this is a -1 standard deviation. That just means that is where about 67% of your data will be. And we'll get more into that, but that's what standard deviation is. How far away from the mean you are. Yes, sir. No, she's in track. No, cross country. One of the running sports. Yeah. Yeah, thanks. I don't know either. Yeah. All right, no problem. All right. We'll get further into details, but that's what standard deviation means. And so for a reader, if I say, hey, this data is one standard deviation away, then I'm like, okay, it's within majority. But if I say, hey, this data is 3 standard deviations away, which is like bam, bam, like way over here, we're talking like it's really skewed out there because that's going to be 99.7% of your data, and it's really out there. All right. So that just gives us a more statistical meaning. All right, so it says data variation is based on the difference between each data value and the mean, and this is called a deviation. So that's kind of where I was getting at. So this is called a deviation. And the deviation of 10 from the mean of a sample of time of fading a brand A would just be 35, which is the mean, minus 10. So then that is now 25. And it can go the other way too. It could be also plus 10. I don't know if it's going to tell you that. It did not, but it could be plus 10 as well. So this is really like a plus or minus. So that means on this bell curve, if this average is 35 and I want to know what is, and I find out the standard deviation is 10, then all of my data 67% of my data would fall between 25 and 45. That's what that all means. And we'll get further into detail there. But if I say, hey, what's one standard deviation away? If standard deviation is 10, I'll teach you how to calculate it as well. It's getting a little ahead of ourselves, but I think it might be nice just to see that graphically. All right, so not get too far ahead of the story. Let's continue on. So it says the sum of the deviations of all data values in the population about the population mean without rounding will be 0, because eventually you'll need to get to a point where you're at 0 and whatever the other value is to make it 0. So -1, 1, -2, -2, and so on and so on. To eliminate this problem, we square the deviation as the squares and find the mean of the sum of the squares by the total number of values. This is called population variance, symbolized by this little cherry. What's it called? I think it's a lowercase sigma, actually. And this is how I write it. I literally just put like a circle, and when I get to the tip there, I just add a little line to it. But that's called, I think it's a lowercase sigma. But variance, and this is very important, is sigma squared. However, this measures is the square of the units measured of the data. Statisticians take the square root of the variance and call it the population standard deviation. So it's just a cherry or a sigma. So variance, sigma squared, standard deviation, square root. So both of these formulas are pretty same. So the standard deviation is just going to be the square roots. Go ahead. What happened? What's this one? Oh, on your homework? Yeah, that's fine. No, that's perfect. But now you know. I actually think it's kind of cool that you'll get ahead so that you can see the questions you need to know. Oh, perfect. That's what college algebra said last semester. So that's why I really like Alex. Yeah. Yeah, I just think it helps. It's because it to me, those are the same type of questions y'all saw on the test, right? That's where I pulled it from. Good to know. All right, so again, so we can see here that the variance formula was just the sum of the mean minus every single one of their averages. So this was the sample mean minus the population mean divided by ever how many there were after we squared them all and then summed them, and we get this equation here. So again, so big X, each individual data value in the population, big N, population size, depending on how it is, and this little n, population of the mean. You also see little n too, just really depends. Little n represents, remember, sample population. Big N, big X, and stuff like that. Those will represent your population. So that would be how you calculate the variance, and then you just take the square root of the answer for the variance, and now you got the standard deviation. All right. So thus the population and variance is this guy, and this is the equation for standard deviation. So here is the two things you must know. I do not supply formulas on your test. All right. Now, granted, the math I'll make you do will be like 10 numbers, so it's not like you're going to do 100. But there you go. All right. So then it keeps going on in our story here. And it says normally these parameters are calculated using technology because it can get time consuming. So if I make you do it on the test, like I said, it'll just be like 5 to 10 samples places. So you're not doing too much of it, but I need to know if you know how to do it. So typically if we're doing like 100, I'm throwing this in like an Excel sheet, an Excel or a Inspire or something, or yeah, an Excel sheet. This works so much faster because you can just set the formula once, copy and paste all the way down, and it gives you all the answers. So when we get to that point, I'll definitely show you that. So again, we normally use technology to do this. Round the population standard deviation to at least one more decimal place than the original data. So if you're given by tenths, just go to the hundreds. If you're given ones place, like it's just a whole bunch of solid numbers, go to the tenths, right? So just go one more place value than what your original data was, just to have a better calculation. All right, so sample variance and sample deviation is the same as your parameter variance and deviation, but now you're only doing part of the population and not the whole population. So more often, the sample standard deviation is used because sample data is available more often than an entire population, which we have seen. The formula for the standard deviation is used to estimate the population standard deviation. However, merely using the sample mean of the sample mean, remember it's X with the line over it, instead of the population mean, which is just the mu, and the sample size N to represent sample size, and then capital N for population size. This would underestimate the population standard deviation. Therefore, to calculate an unbiased estimate of the population variance or population standard deviation, we're going to divide by n minus 1. So we're just going to drop down by just 1 to try to not skew what the population should see, right? Someone came up with this assumption, and it statistically has been working out for us. So they were doing n and really skewing their data from their population from their sample they got. And then someone found out, well, if we just do n minus 1, our data looks a little closer to the population. right? You do not have to do that for population. So if you're doing an entire population, you would just count them all up. But for sample population purposes, we're just going to take, if there's 20 of y'all, I'm just going to go 19. But if I'm doing the entire school 500, then I would still keep it at 500. Does that make sense? All right. We're at the N. Uh-huh. That's a different formula. Variance would be the same thing. You shouldn't be multiplying N times N1. Oh, sorry. That's what we'll be getting to here next. Yeah, we're getting into that. I was like, that's not what you do for sample and population here, but there is a different way to do that. Yes. All right. So here we go. So you can see here that the N-1 concept. Some people do use the S for standard deviation. So that's another notation you might see. This right here is the same thing. Well, this right here, sorry, this would mean this sample standard deviation is just an S, but a population, I'm just going to do ST for standard deviation, is the little sigma. All right, so just like, so same concept as before, where population's all of the Greek letters, and then we saw that sample was all the Roman letters. Now I don't know what S is as a Roman letter, but I think they're trying to keep at least the Greek with the population. Right. And so then the square root of S squared, which is the variance, and then here's the equation that follows. So same process, just get N-1. And really, this is actually a misprint, so y'all might want to add this in, but it's, you need to subtract it from your mean there. So there should be a line over these X's here. Because obviously, if you're just going to take the sample minus the sample, that would be 0. But you're taking whatever the sample is minus the mean of the sample population for each one of them, and then squaring them, then adding them all up. All right, so to get to your question, let's look at the next example. So to find the standard deviation for brand A, we're going to find the sample standard deviation for brand A from example 3.9, and we're going to do this tomorrow. All right. So we're getting there. We're getting caught up.